Great, thank you very much. Oh, yeah. I know it's.
You've been using this one, right? So
Right, okay.
we can stick with this one.
I hope people can hear me. So what I want to do today is to finish this proof of Iwasawa's theorem but remember I want to prove what I call theorem A. So let me remind you what that is. And so now we have, again, the base field F is an arbitrary finite extension of Q, and now I can take any ZP extension F infinity over F. Theorem A we will prove for an arbitrary ZP extension. In no way do we need its cyclotomic one. And the usual notation, gamma is the Galois group of F infinity over F, and Fn will be the nth layer, and so on. And as in the past, An prime will be the p primary subgroup of the prime In prime mod Pn prime. The prime indicates that always we throw away all the ideals dividing P, whether they're ramified or not. Because it needn't be in this extension that every prime about P is totally ramified. I don't need that assumption at all. So now, I have these An primes for every level of the ZP extension, and you have, when n is less than or equal to m, we have these two very basic maps, namely there's the map INM, which sends An prime to Am prime, which of course, as I remarked yesterday, is certainly not always injective in general. And then there is the map, the norm map going the other way, norm of Mn from Am prime to An prime. In fact, of course, it is surjective once there is a totally ramified prime. We'll be analysing that more fully later. So now what you can do, you see, is you can take, with the maps In, you can take the inductive limit of the An primes, and this gives you the map A infinity prime. This gives you the module A infinity prime, which is a discrete gamma module that I've been talking about in the past. And then the other way, with the other ones, we can take the projective limit with respect to the norm maps, and that way I will get a compact gamma module, which I will call W infinity prime. And now so curiously, what we want to do theorem A was actually, in the cyclotomic case, it was that the homomorphisms of A infinity prime into mu P infinity is a torsion lambda gamma module. That was the exact statement of theorem A. But as usual, the fact that you have mu P infinity there, this twisting by roots of unity, that in fact, if I write now Z infinity prime for the homomorphisms of A infinity prime into QP mod ZP, then this Z infinity prime will just be the homs, it'll just be this Z infinity twisted by the tape module. Because again, that if you have a finitely generated, it's a purely algebraic remark, finitely generated lambda gamma module, which is lambda gamma torsion, if and only if its any tape twist of it is also lambda gamma torsion. It's just a simple exercise. So it suffices, in fact, to prove, so what we want to prove is that this module here, Z infinity prime, Yes, Z infinity prime is lambda gamma torsion. Now the curious fact is that it doesn't seem easy to prove that directly just working with ideal classes. I mean, the reason for that is that in fact, the co-kernel of the map from AN prime to AN prime fixed by the Galois group, that is not very easy to control. So I don't think that that one can, in general, because remember we're working in complete generality here, one can hope to prove that this module Z infinity prime is lambda gamma torsion in a direct way by just looking at its gamma co-invariance, of course, which would gamma n co-invariance, which would be the Homs of the A infinity prime gamma n's into QP mod ZP. So that to carry out the argument, which is the strategy Iwasawa uses, we have to take a different approach. And the approach is to use this other module, W infinity prime, which is the projective limit of the AN primes. And it's by studying this module and eventually the connection between the two that we can prove the theorem. So the reason why we can carry out this argument is that, so that's the, so the argument now breaks up into two parts. That firstly we're going to show that W infinity prime is a finitely generated torsion lambda gamma module, and the second part is that we're going to explain, and it will turn out to be, it's quite elaborate, quite an elaborate bit of algebra, but we will show that in fact there is a simple relationship between W infinity prime and this Hom A infinity prime QP mod ZP, the Z infinity prime. And so there are two separate parts now to the argument that follows. So the way to study W infinity prime, of course, is to interpret it as a Galois, and then argue a little in the spirit we will begin to argue for the extension M infinity over F infinity. So now the relevant extension I want to take is the field L infinity prime over F infinity, and by definition, it's the maximal abelian P extension of maximal unramified abelian P extension of F infinity, in which every prime of F infinity above P splits completely. The fact that we're working all the time with these prime things means we always have to have the split completely condition involved. In fact, in Iwasawa's paper, he also carries out the same entirely analogous argument where you work with, you drop the split completely condition. It's the same arguments work in both cases. So now let's look at the nth layer, f of n. It will also have an analog. It will have the field Ln prime, which is by definition the maximal unramified abelian P extension of Fn, in which every prime above P splits completely. And of course, by class field theory, the Galois group of Ln prime over Fn is isomorphic to An prime. So I claim, in fact, that my W infinity prime, right, the projective limit of the AN primes, is indeed the Galois group of L infinity prime over F infinity. This translates this module then, therefore, as a Galois group. And, well, what is obvious is that the L infinity prime must be the union of all the Ln primes, right? Because obviously every Ln prime, when you translate it up to F infinity, will be contained in L infinity prime. And of course, any element of L infinity prime will actually be defined over some finite extension. It was defined over F infinity a priori, but there's only a finite number of coefficients in its polynomial, so it will be coming over Ln prime. And of course, the Artin map tells us that AN, by class field theory, AN prime is always the Galois group of Ln prime over Fn. And let's just recall what happens, you see, when we vary n by class field theory. So let's take the situation now. We know, of course, that because the empty closed subgroups of gamma are isomorphic to ZP, and the only primes that can ramify are some primes of IEP, perhaps not all of them, that there will be some integer n naught such that from that point onwards, every prime which ramifies in the extension will be totally ramified. So that's what the integer n naught in all that follows will be. That all are totally ramified in F. And so if I take any m greater than or equal to n, and greater than or equal to naught, then obviously the intersection of Ln prime and Fm, because Fm over Fn is totally ramified, that must be Fn. And so the Galois group of Ln prime Fm over Fn will be the same as the Galois group of Ln prime over Fn. And by class field theory, right, the basic properties of the Artin map, we therefore have the norm map here will correspond to the restriction map here. And so to get the final result, we just pass to the projective limit for overall n. All m greater than or equal to n naught. So we now have to, actually if we're going to prove the first part now, we can forget about, we've just got to show that this Galois group of L infinity prime over F infinity is a finitely generated torsion lambda gamma module. That's what we have to show. Now, we argue as before, because you see the field we have to see it, we have to study quotients of the Galois group of L infinity prime over F infinity. And so we now we define script Ln prime. So notice here it's a curly Ln prime, it's not the Latin Ln prime. It's by definition the maximal Arbian extension of Fn in L infinity prime. Now the crucial thing to remember is that this curly Ln prime cannot be equal to Latin Ln prime. It certainly contains it, that's obvious, but it can't be because the curly Ln prime contains F infinity. I mean, it's infinite. Ln prime obviously contains F infinity, and so they're certainly not equal. And I mean, in fact, it's even not true in general that Ln prime is Ln prime F infinity. So we have to analyze more carefully what is going on here. And let's recall that W infinity, by definition of the curly Ln prime, of course it's the maximal abelian P extension of Fn contained in L infinity prime. So this Galois group of Ln prime over F infinity, just by the very definition, will be the gamma n coinvariance of W infinity prime. So the whole point of the argument now, we want to try, remember, from the structure theory, we're interested in the behavior of the ZP rank of W infinity gamma n co-prime, gamma n co-invariance as n gets large, as n goes to infinity. So we might as well assume that we're in the situation where n is greater than or equal to n naught, which is what I'm going to assume now. And you see, from n naught onwards, there is a fixed number of primes ramifying, right? Because they're all totally ramified up from then on. And so I'm going to write S for this fixed number. S is the set of the number of primes of which ramify in this extension. And let's note that, of course, in Ln prime over Fn infinity, all primes above P split completely. So in other words, we know the total ramification. This is the whole observation to make. We can work out the ramification of, so let's let's spell it out further. W1 through Ws will be that those primes of Fn which ramify in Ln prime. And you see, because these primes are totally ramified in F infinity, and then they split completely even, they're unramified after that, and the Galois group of F infinity over Fn is isomorphic to Zp. This means if I write T1 through Ts, capital T1 through Ts for the inertial subgroups of these primes in the Galois group of Ln prime over Fn, then in fact the Ti for every I must be isomorphic to gamma n, which is isomorphic to Zp. Remember, we have this picture here like this. And so, and remember, Ln prime, essentially by definition, is the maximal unramified extension of Fn, which is contained in curly Ln prime, just essentially by definition. And therefore, it has to be the fixed field of the subgroup generated by all these inertia groups. So, in other words, that tells us that the Galois group of curly Ln prime over Ln prime must be this subgroup generated. This is all an abelian situation. T1, 2, 3 to Ts. And of course, we don't know whether these inertial subgroups are independent or not, but what is obvious, since there are just S of them, is that follows therefore that the Zp rank of the Galois group of curly Ln prime over Ln prime is at most S. But since the Galois group of Latin Ln prime over Fn prime is finite, this tells me in fact that the Zp rank of the Galois group of Ln prime over Fn is at most S. And then since the Galois group of F infinity over Fn has Zp rank 1, we conclude that for all n greater than or equal to n naught, the ZP rank of the Galois group of Ln prime over F infinity is at most S minus 1. So what we've actually proven by this is that for all n greater than or equal to n naught, the ZP rank, because remember this Galois group here is by the definition of the gamma action, is in fact the same as W infinity prime gamma n coinvariance. So we've actually shown that this ZP rank is at most S minus 1 for all n greater than or equal to n naught. And of course, each of these gamma n coinvariances in any case a finitely generated ZP module, so there's no question of the W infinity prime not being a finitely generated lambda gamma module, and so by the structure theory we immediately get the corollary that it is a torsion lambda gamma module. So this is the proof of the first part of the proving the whole theorem. Now, for the second part, the situation is a little more intricate, but I want to try and explain the details. So we have to work out a relation between W infinity prime, which is this Galois group as a lambda gamma module, and Z infinity prime, which is just this Pontryagin dual of the Homs of the inductive limit into QP mod ZP. And I have to work out a relationship that will enable me to deduce from the fact that W infinity prime is lambda gamma torsion, that the same will be true for Z infinity prime. So let's bear in mind the following, and it's rather intricate, this part. I hope to try and at least explain some of the essential ideas. That, of course, for n greater than or equal to n naught, the extension f infinity over fn is totally ramified, right? There's at least one prime which is totally ramified. So that means, and this is a ln prime over fn, everything is even, it's unramified, and in fact the primes above P are splitting completely. So when I translate that up here, this Galois group here will be the same as that Galois group there, obviously. So this means that an prime, which is what this Galois group here is isomorphic to by class field theory, is canonically isomorphic to the Galois group of f infinity ln prime over f infinity for all n greater than or equal to n naught. So now because of this fact that all these nice things are only happening for n at least n naught, then you have to, we want to now introduce a certain submodule of the Galois group. So I'm going to define V infinity prime. I'm sorry, I'm just running out of letters to call these things, but it will be the Galois group of L infinity prime over and now this is an F infinity here, but I translate F, I take the compositum of F infinity in L naught prime, Ln naught prime. So remember, Ln naught prime over Fn, over F infinity is a finite extension, so this is just a submodule of finite index in the whole Galois group that we're interested in. It's a submodule of finite index in W infinity prime. Now, it's convenient at this point when I have to talk about the relationship between the various modules to think of lambda gamma as the formal power series ring, ZP double brackets T. We've seen this many times. This is, pick any isomorphism which maps a topological generator gamma to 1 plus T. And then I'm going to write, following Iwasawa, W omega n, this is, I guess, is 1 plus T to the P to the N minus 1, which is the same, of course, under this isomorphism as gamma to the P to the N minus 1. And since gamma to the P to the N generates gamma n, this tells me that, in fact, for any module M, the gamma n coinvariance is nothing other than M over omega n M. And it's also obvious that if n is greater than or equal to n naught, then omega n naught divides omega n. And so the ratio I'm going to write following, again, Iwasawa, mu n naught n. So now, I'm sorry, this argument's a little bit intricate. At least I want to point out the essential things. The sort of crucial lemma is that for n greater than or equal to for n greater than or equal to n naught, I'm suddenly worried myself. I think this should be Well, I'm sorry, there is some point, I mean, I claim here in this lemma that Ln prime is Ln prime F infinity, which would imply, now I think, I'm suddenly bothered about why that is true. But in any case, well, let me go on. What is certainly true is that the Galois group of L infinity prime over Ln prime F infinity should be the mu n naught n V infinity prime. Remember, V infinity prime is this subgroup here. I think I've got one of these Galois groups. This is not quite correct, I think, but this statement here is certainly correct. That the Galois group of L infinity prime over Ln prime F infinity is the mu n naught over n V infinity prime. So therefore, so I'm afraid we should just accept that. I've just forgotten. I think there's something not quite right in my statement of the lemma there. But in any case, this will tell us that An prime, you see, we know that I mean, it's certainly true then that An prime is W infinity prime, is this quotient here of by mu n naught n V infinity prime. I mean, somehow the point here is that in the V infinity prime you absorbed all the extraneous zeros that could be coming in, but I'm afraid I've been sloppy about the details here, and in fact, but this statement is correct. In fact, there's An prime over W infinity prime mu n naught, and moreover, what happens as you vary the n? So if n is less than or equal to m, then you get, so you have the inclusion map An prime to Am prime. And on the other hand, over here on this side, the way in which you go up from this quotient to this quotient, because this is a multiple of that, is you have to multiply by mu n n. So this is the integrate part. I'm sorry about the details here, but this is the integrate part of Iwasawa's argument. And therefore it follows, now let me, so if this diagram is certainly correct, and it follows therefore that A infinity prime, which is the inductive limit of the An primes, will be this curious inductive limit here of W infinity prime over mu n naught n V infinity prime. You just take the inductive limit of those. But let's remember, so remember here it's W infinity prime, which is the whole Galois group, and V infinity prime is this subgroup of finite index. And now it's obvious, it's a general algebraic fact, that because the index is finite, this inductive limit here is the same as the one in which you took V infinity prime over mu n naught n V infinity prime. And so what the conclusion, so therefore we've shown that A infinity prime is given by this inductive limit. And therefore it follows that Z infinity prime, which is the Pontryagin dual, Pontryagin dual will change the limit the other way, and so we get that it's the projective limit of the V infinity prime over, say, pi n V infinity prime, QP mod ZP, where pi n is the mu of, well, I've just changed the notation, but n naught to n naught plus n now, to have it for all n greater than or equal to naught. So this is this rather strange relation between Z infinity prime and V infinity prime. They're both compact lambda gamma modules. And I mean, I'm sorry, I'm sloppy about some of the details in the middle, but this is what Iwasawa shows, and we have to conclude what we know, of course, is that the W infinity prime, we've proven that that is a torsion lambda gamma module, and so we want to conclude somehow, and therefore the V infinity prime is, it being a submodule of finite index, so we simply want to conclude from this something about Z infinity prime. But on the face of it, it looks like nothing on Earth, right? I mean, you carry out this strange algebraic construction, you end up with this strange limit. So here's where the idea of adjoints come in. That, remember, well, okay, let me say it here, that if I now, so now it's some pure algebra to finish the proof. And the pure algebra is as follows. So let's let X be any finitely generated torsion lambda gamma module. And let's assume that X over pi nx is finite for all n greater than or equal to naught, which certainly was what we had here, because it was the an primes, where pi n is given by these new n naught plus n's. And then you can look at this strange limit of the Helms x pi nx into qp mod zp, this projective limit, and what is true is that that is the adjoint of x. This is pure algebra. Now, as I was briefly explained earlier in my lectures, the adjoint, the conceptual way to define it is to say that it's thext. Right, the xt1 of lambda gamma x lambda gamma. And it's in no way obvious that this conceptual thing here, which is the one I gave you, is the same as this description here. But in fact it's true, and someone pointed out to me it was, as I say, it's in this early work of certainly Bio and Paramariu's. Paramariu's work is published, but there's a good discussion of this, I gather, also in the book Galois Homology of Number Fields by Neukesch and Wingberg and so on. So there is if people are interested in the details, you can certainly you can find them in the readily available literature. But Iwasawa himself, in his paper, he just defined the adjoint this way. And I mean, the remarkable thing about the adjoint is that the adjoint, of course, of a finitely generated torsion lambda gamma module is another finitely generated torsion lambda gamma module. So that's the first thing we conclude now. Finally, we have shown, therefore, that Z infinity prime is a finitely generated torsion lambda gamma module. But also the beautiful thing about the adjoint is that which is pseudo-isomorphic, of course. I forgot to say it here. It's pseudo-isomorphic to X itself, but it has this nice property that it has no non-zero finite submodule. And that is so that therefore we conclude that this always, for any ZP extension, this homomorphism of A infinity prime into QP mod ZP has no finite non-zero gamma submodules. And so that finishes the proof of theorem A and the proof of Iwasawa's theorem. And since I've got a few minutes left, why don't I just now let me put this. No, 12 and 11. So now if we go back to our cyclotomic ZP extension F infinity, and then we had n infinity prime here, and then down to f, we saw from our argument in the previous lecture that we determined that this is in fact that this Galois group has no, so the Galois group of m infinity prime over f, excuse me, this is nonsense. This is m infinity here, and here we have f infinity, has no ZP torsion. That's one thing that emerged from Iwasawa's proof in that case. And in this case, we have shown that there is no non-zero finite lambda gamma submodule. So the two facts together imply, of course, that the Galois group of m infinity over f infinity has no non-zero finite lambda gamma submodule. Because if there was one, its intersection with this subgroup would have to be zero, and therefore would have to inject into the quotient, and therefore there would be torsion in the quotient. So there's a very nice property that Iwasawa points out of the Galois group of m infinity over f infinity. And by the way, this is not true at all for the Galois group, say, of L infinity prime. This is a very special property of modules. It's not true at all for the Galois group of L infinity prime over F infinity. There really are, in some cases, finite submodules. But as I mentioned earlier, nevertheless, so this tells us, of course, now where are we? This tells us that we have a nice exact sequence. Naught goes to x of f infinity, which is this Galois group of m infinity over f infinity. It goes into lambda to the R2, to the degree of f over q divided by 2. This map's injective now because there is no non-zero finite submodule, and nevertheless it's not always free. There is this co-kernel here which is finite. D is finite. And D is sometimes non-zero, and it's a very subtle invariant, which, as I say, also turns up naturally if you look into the K theory of these number fields after tau. Okay, well, I'm afraid I'm finishing fairly early. That, as I say, this whole theory is sort of striking that we can't prove this for another, the fact that the boundedness of the Leopold defect at the moment for any other non-cyclotomic ZP extension of F is a sort of humbling thing that you would think that because Iwasawa had this beautiful proof in this case, there would be others. But even the very simple cases, the simplest animal, I shouldn't say simple cases, we don't know how to prove it. If you take an imaginary quadratic field and a prime which splits in that field, then class field theory tells you there's a unique ZP extension of the imaginary quadratic field, which is unramified outside Gothic. Take one of the factors, say Gothic P, and then you can translate that over any finite extension of the imaginary quadratic field. So this is an extension now over, right, you have a K and a K infinity, a ZP extension, and you go to an F and an F infinity here. So just by translating this up, and this is a ZP extension which has a lot in common with the cyclotomic ZP extension. For example, in this extension, there are only finitely many primes above each rational prime. Of course, this is not true for an arbitrary ZP extension. You can have primes splitting completely and so on. So this is would be the obvious case to try and tackle the analog of the weak Leopold conjecture, and one can get evidence for it, prove it in a few very special cases and so on, but the general proof is completely lacking, and it would be very interesting to do it. So I've just attempted in these lectures to try and explain a little of this beautiful paper of Iwasawa's. By the way, perhaps I should say the whole latter paper, part of that paper, he is attempting to, he constructs an analog of the Riemann bilinear form on toruses. And so far, no one, and the trouble is that we don't know so far any, he constructs it on a space and free ZP module, QP module, but we don't know so far any example where that space is non-zero. It may well be that there are examples, but we don't know any examples. But the fact that Iwasawa took a long time to beautifully construct this bilinear form and show it has all the properties that you'd expect the analog of the Riemann form, certainly makes one think that he felt that there should be interesting applications. But no one has found any yet. So maybe someone will, I hope so. Thank you.
Any questions?
I was just wondering in that sequence, so this is the Galois group with the maximal unramified unramified outside P abelian pro P extension, right?
Yes.
So why should it inject? Are you making any assumptions? I mean, why should it inject into the reflexive?
No, because I just proved it had no finite.
Yeah, but it could have a torsion submodule, right?
Oh, yeah, you are so absolutely right. I should say this is X over torsion submodule. Excuse me. Yeah, I'm just. Romeo's absolutely right. XF infinity divided by its torsion lambda submodule. Thank you, Romeo. Yeah, I'm not thinking. Of course, that's correct. Yeah. Yeah, I mean, it's the torsion part is of course very interesting because that is related to the complicated questions in many cases. Yeah.
Other questions?
But just before, why was the fixed field of L infinity prime under gamma n the same as L curly L n prime? That was
no, this is, yeah, I mean, you see, I must confess, when I was taking the notes, I mean, it's, Yeah, I mean, it is, you see, it's, no, I'm sorry, I should consult Iwasawa's paper you see, he doesn't prove this statement, I have to confess, in his paper, because he just refers back to one of his earlier ones. And, but it's certainly true what I'm claiming here. I think there's no doubt about that the Galois group, U, N, naught, N, V, I mean, this is what he asserts in the paper. So that look, I'm sorry, I better dig that. I'll have to dig it out of his paper to be sure of that point. Yeah.
All right. Well, maybe so people go on their way to the field trip we should end there. But let's thank John Coates again for the wonderful.